Hi, my name's Alexander Rengel, and this is Lab 5 for Physics 2211. So, for this lab, we wanted to model the two-dimensional projectile motion of a paper ball opposed by drag force and how this differentiates when working with in one dimension. This lab models and showcases velocity update, position update, and drag force. The drag constant found in this lab is 0.9 times 10 to the negative third. The system of this lab is considered to be the paper ball while the surroundings are the earth and the air around the ball. The mass of the ball is 0.004 kilograms with an initial velocity of 2.47 in the x, 2.5 in the y, and 0 in the z meters per second. An initial position of negative 0.216 in the x, 0.342 in the y, and 0 in the z. Experiment. For the experiment portion of this lab, I threw a paper ball with a range of unknown or of known dimensions or of unknown dimensions. I videoed this and used the tracker to locate the position of the ball at each time interval. These are the graphs that were made from the tracker. So we got in the x direction position over time, and then we got the y position over time. As you can see, this one's more linear and this one's like increasing and then decreasing. So we got the coding without drag, and we got the coding with drag in this one. So I'll give it a second for y'all to like watch. Or not watch, but like see the difference. And then here are the graphs with and without drag. So we got position versus time for both of these. And as you can see, we got velocity versus time. And right here, the velocity is constant. So it doesn't change when it's without drag. So this side is no drag, this side is with drag. And right here, you can see the velocity going down slowly when it has drag. But all the other ones are roughly the same. This one's a little bit more curved than this one, but other than that, they're. And then this one has a lower ending velocity. So the drag force that worked best was found to be 0.9 times 10 to the negative third, and then the sources of error in this lab could be due to the shooting angle of the video. Due to not everything fitting into the frame, there's a small angle which can slightly impact the tracking of the x and y axi. So my what if question: what would happen to the graphs if a greater initial velocity was used? In the x direction, the velocity graph would taper off quicker because drag force slows down the velocity in the x direction. In the y direction, the velocity graph would look similar but with greater magnitude. While the ball is in descent, due to the ball being higher than before, it's possible for the ball to reach terminal velocity. In this lab, terminal velocity was never reached due to the short distance in the y direction. Because terminal velocity comes after a certain amount of time in the air, the terminal velocity was never reached because the ball was not in the air for that long. Importance. What does terminal velocity mean and how does it relate to the experiment? Terminal velocity is when the force due to gravity is equal to drag force. What this means is that there is no acceleration in the y direction and something falls at a constant velocity. So when something reaches its maximum velocity, and just is at that velocity for the rest of its free fall. So that was my lab 5, and that's it. Thank you.